This is Spencer Snowling from Hatch, and I'm glad that you can join us today for our monthly GPSX webinar. Today, I am joined by my colleague, Jacob Barkley, and Jacob and I will be talking about various features that you can use in GPSX to do advanced visualization of your modeling results and your data so that you can easily communicate some of the more complex aspects of activated sludge to the ultimate end user of the results of your simulation efforts. So as per usual, we will ask you to type any questions that you might have as we go along the way into the chat. And then when we get to the end of the webinar, we'll hang around and answer any questions that you might have for 5 or 10 minutes at the end. Okay, so the plan for today is that I'm going to talk a little bit at the beginning here just about the background of like the types of outputs that we use in GPSX and how you can best visualize the model results that you have and how to incorporate the data that you have. There's a lot of functionality that's already built into GPSX, so I'm going to cover that with our built-in visualization outputs first. I want to give a little bit of a special look at the statistical goodness of fit analysis tools that we have available in GPSX. And then I'm going to hand it over to Jacob, who will then talk about creating your own custom graphics using Python. So Python, as you know, is a plugin into GPSX, and you can use it to drive the simulations and collect and post-process them, the results, and create any new sorts of graphics that you might like, things that we don't normally have built into GPSX already. Okay, so I'm going to jump right in. So during the regular type of simulation work that you would be doing with GPSX, I'm sure you've noticed that GPSX really produces a huge amount of information. It's actually one of the challenges that we've had over all these years of developing the software is to like sort of wrangle and handle all of the numbers that you get out of the software. There's probably 50 or 60 concentrations at every one of the connection points in your layout on the drawing board. So that information can be then captured, and you want to be able to plot it in a way that makes sense, easy for you to understand, and then you want to be able to export that. So we've put together, of course, the tools that you're used to seeing when you use GPSX, our bar graphs and tables and so on. And we've sort of tailored those for a couple of the most common uses of the software. So, for example, if you're just doing a regular steady state design type solution to the model, I'm just going to run it to steady state, see if the tanks are big enough. What you get out of that is at the end of the steady state solution, you have one set of values for everything in the model. And that's what the plant is running under equilibrium conditions. So you might want to plot, a bar graph like this that shows you the profile of ammonia. I'm sure you're familiar with the quick panel graphs that come up. They're tables of details of information where we've kind of stripped it down to just the most important stuff for each one of the individual units that you have here. Right. So now for dynamic simulations, however, when you're running something where things are changing over time, what you're getting is like all of those numbers, those hundreds and hundreds of values that are going to be calculated. That's going to happen for every communication interval as we run through the length of the simulation. So it is infinite, many orders of magnitude, often more orders of magnitude more information that gets kept in memory and that you can have access to at the end of the simulation and export that out. So this amount of information is actually somewhat controlled here by the communication interval. So at the bottom of GPSX, where you set the stop time for your simulation, if you click on the word stop time, you get actually a little pull down menu there. And if you flip over to communication interval, you can tell GPSX, this is how frequently I want you to report the results. This is different than the actual time step of the model. In the background, the model is being solved in discrete time steps as it moves forward in simulated time. That time step is very small. It's probably on the order of 10 seconds, something like that. But we don't need to report back the results that frequently. So we have this tool that basically says, once an hour, give me the results of wherever the model's at on the hour. And then it does that frequently. So if you're running a very long simulation, you may only need the results once per day or once every 6 hours or something like that. If you're running it very, very short, though, like say you were having maybe some sort of advanced aeration control, you may need to run it at a very short interval in order to see the dynamics that you want to see. This can also be an issue when you're doing SBRs as well. I want to see all of the things happening inside one cycle that might only last for 20 minutes. So therefore, I want to be able to plot that on a much more frequent basis. Come here to this menu and adjust the communication interval to whatever you need it to be. Just be advised that if you set it to something really small, like 5 seconds, it's going to make your simulation run much, much slower. Okay, so this means ultimately that there's a lot of information to manage when you are using GPSX. Basically, one of the challenges that I found over the years is sometimes if you're doing a specific kind of study and you're trying to show, this is the effect when you dose carbon here or whatever, those things require presenting your data, presenting the simulation results in certain kinds of ways. And it really does vary sort of from simulation task to task, right? Highlighting this particular aspect of the process. So for that reason, we have a large number of different ways that you can plot simulation results and data on various types of graphs. So if you ever wondered why, if you click on the graph type and we've got 9 different ways of doing it, that's partly the reason. Is sometimes you want to be able to have a profile of something. Maybe sometimes you would like to have it as a time series graph, or sometimes you need to have it as a scrolling window. Those things are all there to be able to help you tell the story in the way that you need to. So it's going to use the results, but you get lots of different ways to display it. The quick panels themselves were designed to be able to strip down the massive amount of information for, say, a plug flow tank down to just the 10 or 15 things that we think people would typically want to see when looking at a BNR system. Ammonia, COD, phosphorus, airflow, OTR, that kind of stuff. So those are there. The tables that you can plot, you can click on the button. I'm going to come back and show those in a minute here. Those are like customized things that you can sort of decide which things you want to be in the table. And then we have these various visualization tools. This is what I would call the more advanced stuff. So the Sankey diagram, the mass balance tables, and the energy summary. And then all of that is what's built into GPSX. And then you can take a step beyond, connect Python to GPSX, collect all of the data from the simulation, and then you've got all of the plotting types of libraries that are available in Python to be able to plot whatever type of graph that you like. And you can be very creative and take advantage of all the great stuff that's out there. So today's webinar is really going to focus on these two. I'm going to have a few slides just to talk about the first few that are there, but then we're going to spend most of our demonstrations today talking about the advanced visualization tools that are built into GPSX, and then I'm going to hand it over to Jacob, and he's going to talk about what other interesting things you can do with Python. Right. Okay. So typically when you're running a GPSX simulation, if you're doing a dynamic run, you're typically plotting the simulation results, which is the solid line here, alongside some real data points like these. So if you have that data, you can plot it alongside the graph, alongside your simulation results. And that's, typically what you would do if you're doing a model calibration to a real plant. Now, if you're new to GPSX, I'm just going to take a moment here to mention that you should look at tutorial 6 that's in our tutorial guide. You can get that from the help menu, or you can go to our YouTube channel and watch this video here on how to do it. These things are, it's a nice and easy, straightforward way to get GPSX to read the Excel spreadsheet that has all of your data in it. And then you can move forward and have that data come into and either drive the simulation or plot the results alongside it. Okay, so different types of graphs are available, as I mentioned before. And, we've tried to make these as intuitive as we can. And one of the ones that I use all the time and is the most useful is these bar graphs that basically represent the concentrations in the reactor as we go from left to right. That's generally from upstream to downstream. Those zones in series here can be basically the same thing that you see on the graphs here. I will take a very brief mention here, by the way. If you're new to GPSX, this is showing 4 by default, but actually you can set what number of reactors in series you want. If you need 8 or 10 or 12, you can do that too, and then you'll end up with 8 or 10 or 12 bars on the graphs. But nonetheless, these are like absolutely the most straightforward, the easiest way that I feel to sort of visualize the BNR process. You can see the ammonia going up up, and you can see when we get to the aerated zones, which is where the DO is here, that the ammonia starts to go down because it's being oxidized to nitrate. And look over here, you can see the nitrate coming up. So these bar graphs, completely intuitive, nice way to be able to plot all of that information that you need. We also have things like this, which is the clarifier solids profile. It's basically the same bar graph, but turned on its side by 90 degrees. This is representing these 10 layers, horizontal layers in the clarifier model. And you can see here the very low solids concentrations at the top and higher concentrations, 7,000 milligrams per liter here at the bottom. We also have the grayscale graph. You can see here that this is basically exactly the same information. Instead of moving a bar from left to right, it's basically making it slightly colored from white to black as you go from the the low numbers to the high numbers there. Whatever works for you, you can use those two things to tell the story as well. Now, all of that is great for situations where you are plotting something within a single unit process. But what we need to be able to do as well, and we have an additional tool, is to be able to build a bar graph out of multiple points in your layout that kind of stretches across the entire plant. Like say I wanted to plot phosphorus from the influent through all of these reactors and clarifiers and everything all the way to the effluent. Now, you can do that. You can actually do that by starting to use the table function that we have. And I hope that you've had a chance to take advantage of this. It's a button here called a new table. So you click on this button right here. This is at the top, over top of the quick panels that would normally be generated for you. So click on this button and it'll bring up a menu that looks like this. And what you do is you specify on the left-hand side here, what connection points do I want to include in my bar graph? And on the right, you pick which thing is it that I want to graph at every one of those connection points. So this particular example I'm showing here is from the influent through to the effluent, I want to plot orthophosphate. So you get a table that looks like this. Now the table contains only the connection points that you have specified. And you can always go back and add and remove columns as needed. And it's a nice way to sort of shave down the information to just the things that you'll need. And you'll notice that by default, you get both a concentration and a mass flow rate. So I'm showing it in SI units here, kilograms per day and milligrams per liter. Now, one of the best parts of this is this button right here. I admit that this is slightly great functionality hidden away a little bit. This button right here produces this graph. So this is basically that exact same data that's in your table, but now it's in this colorful bar graph form. So this is a really useful thing to do if you want to kind of expand out your concentrations and bar graphs that you're playing with beyond just a single unit process, beyond a single plug flow tank. You can do that here. Okay, so that's all the regular, what I would call regular normal graphs that you might be using on a day-to-day basis. What we want to focus on for the remainder of the webinar today is what we call our advanced visualization techniques here, and advanced visualization tools. And I'm going to start out by talking about the things that you will find under this eyeball button here. This is intended to be the advanced visualization. It's called additional output displays if you hold your cursor over it. But really, it's about visualizing your model outputs. So I'm going to start here and show you that when you click on that button, it brings down options to do these 4 different types of graphs, Sankey diagrams, the cost and energy usage summaries, and the mass balance diagram. So very quickly, I will explain what those do. If you've never seen a Sankey diagram before, essentially it is a way to represent flow visually. And so what we do is we draw connection lines and then we fill in behind them with a colored line so that we can see your whole layout. And then we look at the value of whatever it is you want to plot on the grams, on the diagram. So here I'm plotting the flow. So we're going to plot that, and the thickness of the line is proportional to the value. So in this case, this is flow in meters cubed per day. And you can see here that this is 4,000 coming in, and then we get a 2Q recycle here. You can see this line is twice as thick as that line. And then that helps you to really visualize how things are put together in your model. Now, this layout isn't too bad. in terms of its complexity, but I've worked on lots of layouts that are a lot more complex than this. And very often when I'm building the model for the very first time and I'm connecting things together and I'm putting in flow splitters and various things, this can be a really excellent way to just do your very first double check to make sure you set it up the way that you thought you did and make sure all the flow is going to where you think it needs to go. So especially if you're doing something complex with controllers or control splitters or PID control loops, this is a really good way to just double check that this works the way that you think it should. Excuse me. Okay, so now you can do that for flow, but you can also do it for many other things as well. So here I'm showing total phosphorus. And in this case, we are doing the mass flow. This isn't going to be in kilograms per day. And so you can see here, for example, we have 40 kilograms per day coming in the influent. Of course, these dark lines and these high numbers here indicate there's a lot of phosphorus tied up in the recycling of the activated sludge here. But of course, when we get to the end, a bunch of that is going to go down here, 73 kilograms per day go down here. We don't lose anything across the digester, of course, because it's phosphorus. It may transform, but it's still in the pipeline there. And you can ultimately see that when we get to the end here, that of that 40, that's 4.65 kilograms goes out in the effluent and 35.3, all of the rest of it is going out into the sludge. And that makes sense. And actually, this is a really nice way to sort of visually represent the efficiency of capturing your phosphorus and sending it out with the sludge. Now, if you had another whole other unit in here, if you were doing struvite recovery or something like that, you could even have another third connection point. And you know, as you change the operation or as the loading or influent characterization changes, you might be able to see the balance between what goes out in the effluent and what is captured into the sludge. I think this is a really nice way to be able to display that. Okay, moving on to the mass balance diagram. This is more or less the same information, but just put out in table form. And it is actually showing you multiple things together at the same time. So you can specify which things you want to show. These are the standard 4 that we put up on this type of a diagram. And then for every one of these boxes, we're displaying the concentration part and also the mass flow part. And so those are kind of the same kind of information that's on the Sankey diagram, except this is kind of like showing all 4 Sankey diagrams together at the same time. So we designed this actually from a feedback that we got from one of our users who he was actually going to the trouble of cutting and pasting images into a spreadsheet and then doing all those calculations and typing the numbers and using this kind of a display. And we went, hang on, let's just make that a tool standard in GPSX, and we have done that. Okay, now I'm moving on to the energy and cost summary tables. These are designed so that you can look at your layout and then really quickly look at any one individual unit process and see how it contributes to energy usage compared to overall in the whole plant. So the things that are colored darker means they're using more. So you have a lot of ability to change things. You can do it for individual types of energy usage, say, for example, just pumping. And also you can get a summary at the end by clicking over to the other tab and looking at this in table format. And then from here, you can actually plot it as a bar graph, a pie chart as well. So you can see here in this particular example, roughly half of all of the energy being used in the plant is used for aeration. Now, the operating cost summary one, it looks exactly the same. And of course, it is using all of that same information about energy, except now we're multiplying it by the price. And then we add the chemical cost to it. And then we also add the sludge disposal cost to it as well. So ultimately, this is going to be dollars, whereas the previous one was kilowatts. So here, but the functionality of the graph is the same. So when you see here, where is all of the money being spent in this plant? This particular one is showing certainly it's in the chemical dosage part here, as we see. And then you can go through and do that same methodology that I mentioned before. Here's a lot of chemical dosage, and aeration cost is still pretty significant too, but by far it's mostly chemical in this particular hypothetical example we made up. Okay, so I'm going to actually very quickly run through some demonstrations of all of this, just so that you can see and know where to click and how that works. So I have a couple layouts that I've put together. This is the one that I'm going to run here. So you can see right now this is grayed out. We actually need to solve the model first. So you can run a steady state or a dynamic simulation. Pardon me while I sip my coffee here. Okay, so now we have a steady state solution, and we can see this button has become active. And now I'm going to click on that, and I'm going to start by showing you the Sankey diagram. So this is a diagram here, as I mentioned, that's showing the flow at every one of the lines all the way through the layout here. And you can see that always follows around. You can fine tune what's showing on the diagram here. You can see we can hide the mixed liquor ones because they tend to be much bigger numbers than all of the others. So sometimes they'll always have the big line. You can control the thickness of the line as well. You can change the color, some of the behaviors of the way that we control how these things get plotted, and so on. And generally, this is a really nice way to sort of display a lot of information very succinctly. So I use this a fair bit, as I mentioned before, when I'm setting up a model for the first time. I've typed a whole bunch of flows in here and there, and I've got these controllers and everything on. I'll run it to steady state and then come and generate this and just say, okay, just to double check, make sure all the flow's going where I think it's going. And this is a nice way to do that. And you go up here, and then I can select some of these other things, right? I can click on the solids. I can click on COD, so we can see here some COD. Now, these are COD mass flows. Now, COD is not conserved, so to speak, through the plant because, of course, we're adding it through aeration and we're losing it. Say, for example, down here, we can see that there's a lot less coming out of the digester than going in because, of course, that VSS is being destroyed and we're losing it out to gas, the digester gas production, which in this case is just leaving the model. Anyway, nonetheless, you can see sort of how that distribution works. Now, I can also plot total nitrogen, of course, also not conserved here because we're losing some nitrogen gas through various places. But phosphorus is one definitely, as I mentioned before, which is conserved. And you can see here of that 40 coming in, 4.65 left through the effluent and 35.3 came out through the sludge. So that's a nice way, and you can modify these things as needed. Lastly, I'll point out these two buttons right here. This is how you export this thing. You can either save it directly as a PNG file to wherever you need it to go, or you can just hit this button and copy it to your clipboard and then paste it into another document. Okay, so now I want to jump over to a different layout called mass balance here. We have many of these functionalities actually highlighted in our sample layouts menu if you want to jump over there and take a look at that. So let's look at this mass balance diagram. Now, when you pop in here the very first time, it will actually pop up the setup wizard for you automatically. So I'm clicking on the button to do it here because I already came in and played around with this a bit this morning. So what this does is it helps you decide what you want to display. And so you click on the various things, what are the particular things I want to show in these boxes and which things do I want to show them for. I'm going to leave it all checked on for now. And we're going to do that. And so you can see here that what we do is we arrange the boxes and they are connected to the various places that they are the concentrations for. And then the great part is I can actually move these around to where I need them to be, or I can just click on the X to get rid of them altogether. So I'm just going to move a few of these around to, places where I'm likely to want to show them. Let's put this one in here. And maybe we don't need this one. I'm going to put the effluent over here. Sorry, influent, I should say. And maybe I don't want that one. And here's the effluent. So there. Very quickly, you can arrange the boxes into whatever way you need them to be. When you save this, your GPSX layout, these positions of the boxes get saved as well. So you can come back and can run simulations under different scenarios, generate this image for any number of different scenarios, and then save all of those results out and put them into a report or whatever it is you need to do with them. At any time, if you want to go back and get access to some of those things that were not shown before, you can just hit that setup wizard and it will bring back all the options for you. So the other few things you can customize here is maybe I only want to show the mass flow, or I only want to show the concentration in these boxes. That's something you can do. Control which variables you want to show, how many significant digits. And again, we have the same export numbers up, or methodologies up here as well. Okay, moving on to my third and final layout for demonstration here. I want to go to this energy one. And I'm going to run a steady state simulation here as well. Right, and I'm going to go back to this button. I'm going to start with looking at energy usage. And as I was mentioning earlier, we show all of these different types of energy usage in the model. So you may remember from other webinars that we calculate a whole huge number of operating costs automatically as part of GPSX. So we want to know how much energy is being used for aeration, for pumping, and the cost is association with many other things as well. So you can see here we have mixing and heating and a few other things. So I can take a look visually and see what's going on here. Now these are two anoxic tanks and followed by an aerobic zone. So that's where there's only aeration here. I can look here for pumping. We got some small amount of pumping here. This is this internal recycle. This amount of pumping, the reason this is the most is because it's pumping the RAS back here. I can look at mixing in the bioreactors. I can look at heating of this one building. You may not be familiar with the building object. It's one that you can put on the drawing board here to represent the use of energy at the plant that's not related to the process. And so it goes up and down with temperature during the year and so on. And then that's kind of like, mixing, or sorry, not mixing, but the rotors, for scraping the rakes on the bottom of the clarifiers or flights or what have you, and you can add it all up as well. So it gives you a feel for, all of that. It's a nice way to very quickly automatically summarize things. You can pop over here, see that in a table. And as I mentioned, you can get this really nice bar graph here. Sorry, I keep calling it bar graph, a pie chart here as well. And you can also export those out nicely. This one over here, I'll just mention really briefly this button right here. This right now is showing you the whole plant divided up by the type of power usage. But if I actually click on this button and then I plot the pie chart the other way, it's sorted by unit process. So we can see the aerobic tank is using up most of the energy. And then here the building has a certain amount and the secondary clarifier has a certain amount and so on. So, might be another useful way to display what you want to show. Okay, and then lastly, I'm going to then also show the operating cost. So now that was previously just energy. This is now energy shown as dollars, including, and then also adding to that the chemical dosage and also the sludge cost as well. So we can see here aeration cost. I can also flip over to the chemical cost and the sludge disposal, in addition to the ones that I showed you already. And then again, same functionality here. I can look at the total for the plant, and I can also sort it by individual unit process as well. So do it this way. So this is information that will always be available. You don't have to do anything special. Just click on the eyeball button, and all of those things are available for you to take advantage of. Okay, now I want to go back to my slides here and talk just a little bit about the statistical analysis graphs that we also have available in GPSX. So any place that you are plotting simulation results and plant data together on the same graph, if you right-click on the graph in the background there, you will find that the statistics menu will be available for you to select. What that does is it opens up a menu that allows you to select other types of graphs that you would like to plot along with this one. And many of those are there to sort of help you get an evaluation of the goodness of fit. How well does the model fit to the actual data points that we have collected? It does a bunch of analysis of the residuals, the difference between the model and the real data. And then also to handle the real data in different ways, treat it as grab samples, treat it as composite samples, and so on. So what you do is you go to the individual graph that you want, you pick the particular signal that we have. So in this case, there's only one on this graph, total COD. And then it opens up this graph, and then you just check off the things that you want to display, and it will start creating those extra graphs for you. And then you can plot them, move them around, put them on tabs, do whatever it is that you want to do with them. And they usually look like this. They have a gray background. And the one that I find by far the most useful one is the predicted versus measured. So for every point in the simulation where you have a real data point, it looks at the model value at that period of time, and then it plots the predicted model value versus the measured value. Now, if it was a absolutely 100% perfect model that predicted everything accurately all the time, all the data would fall on this line. But that, of course, is never going to happen because the models are never perfect. So what you want to have is sort of gathered around this line as much as you possibly can. And in particular, you want to make sure that it's sort of distributed equally on either side. That's kind of going to give you your best statistical fit. One of the other ones I find very useful too is actually looking at residuals versus the measured value. And this tells you sort of when your model's doing well and when it isn't. So in this particular case, it's showing we have very small residuals, meaning it's a good fit when the values are high, but the residuals are larger when the values are low. So in other words, we're predicting the high stuff correctly, but we're not predicting the low stuff as well as we could be. There's a lot of data points down here, meaning we're doing okay some of the time, but most of the times when we run into trouble are at the low end. So that's another handy kind of thing you could work with. One of the other things we'll get that you could theoretically also plot too is this table of goodness of fit calculations. It's fairly lengthy. There's about a dozen different things that we calculate for you here. And these are something that you could keep an eye on while you're doing your calibration to see, whether you are indeed statistically making things better by changing some of the parameters along the way. Okay, I'm going to do a quick demonstration of that as well. This is actually taken directly from one of our sample layout menus, but I'm going to put that over here. And in this case, I have a small plant and I have a dynamic simulation. So you can see here that when I plot, say, for example, this effluent COD number, we run a one-day simulation with some influent flow and concentrations that are changing. And then we have some data that's purportedly from a plant that we're trying to calibrate to. So you can see here, I'm plotting effluent COD, effluent ammonia, effluent TSS, mixed liquor. So you can see here that I have already gone to that statistics menu, clicked off on some of the things that are useful to me, and then it's put these other graphs around it. You can hit that auto arrange button to put them in the right place. And now I can consult these. And every time I run the simulation, it will recalculate all of these things. So this is obviously a reasonably good fit. Right now, out of the box, before we do any other things, this fits pretty well. So effluent ammonia is, of course, another story. We can see just visually looking here that the model prediction is over predicting nitrification, right? The effluent ammonia is much lower than it was in reality. And we can see here we're nowhere near to having our data points fall on this perfect line. So that's one thing to keep in mind. Let's see if we can make some changes to make that better. Let's take a look at the effluent TSS. You might look at this and think that's not too bad, but by looking at this graph, you can see, well, there's certainly a lot more dots above the line than below the line. So therefore, we are over predicting effluent TSS compared to the real data. And what's our mixed liquor look like? Well, it's consistently low. So you can see here that, of course, this is obviously showing that the measured data has some variability into it, but our model prediction is almost always right here around 2,500 milligrams per liter. And so let's see what we can do about making those changes. Right. Okay. So what I've done is in this particular layout, there's some scenarios that have been set up where we're going to take 3 steps to calibrate this model a little bit and bring it in line. So we're going to change the autotrophic growth rate. That's going to affect the effluent ammonia. So we changed the AOB and NOB growth rates here. We backed them off a little bit, knocked them down. That means we're not nitrifying as much. And so now that's actually, reasonably not too bad. We can see we got dots on either side of this line. I'm sure we could play with it a little bit more, and then maybe we could smooth this out a little bit. I think even by just looking at this, we can see here that it actually fits most of them very well. And we have a few of these outliers here that are probably not very good real data points. Those are ones that are probably never going to be able to be matched anyway. Okay, let's take the next step, which is to change the settling parameters in the secondary clarifier, and we're going to update that. So this is going to look, well, more or less the same as we did before, but we're going to get a slightly better fit here in our effluent TSS. So now this has come down. We now have, I mentioned before, most of the dots were above the line, but now they're kind of evenly spread around. So that's kind of helpful to show us that that was in the right direction. And then lastly, we're going to change the influent characterization a little bit, increase the inert particulate component of that. So that doesn't change here. The TSS looks pretty much the same as before. The ammonia is the same as before. That's fitting pretty well, but it does help to bring the mixed liquor up. Now, you could argue that, well, this isn't a really, great fit altogether. This kind of does help to show, though, that, there's a lot of variability in these measurements that probably don't have anything to do with the actual process. So therefore, getting it like this is probably about as best as we could do. All right, so that's a good statistical analysis. I actually did do all the error calculations here. We could have actually taken a look at how these numbers changed, and hopefully some of the residuals kept getting lower and lower as we were moving into the correct values. So these are things that we calculate all the time. If you like to sort of analyze it from that point of view, these are all available for you to plot, and you can always capture these, copy the data, copy it to the clipboard, just like you can anything else. All right, I think if this was a real calibration exercise, I'd probably iterate around a few more times. Now that, of course, changing the influent might change your effluent numbers a little bit, so we might do it again, but nonetheless, that's kind of a helpful thing to do. All right, I am going to hand it over to you, Jacob.
Right, thank you, Spencer. All right, so as Spencer mentioned, I'm going to be going over some of the advanced visualization techniques you can use due to the integration of Python into GPSX. And the reason we added Python to GPSX specifically is so that users can essentially augment the pre-built-in functionality that already exists in GPSX. This can be simulation-based functionality, or as we're going to focus on today, more visualization-based functionality. And you can augment this functionality in a variety of ways. For example, we have the ability now to define custom variables in Python that you can then use in your simulation of the GPSX layout, or you can have those instead be outputs, for example, that you can then take and plot to observe the performance of your plant. It's also very good for introducing uncertainty into your simulations because you can do things like use random number generators to create a distribution of inputs to simulate. And that'll give you a distribution of data that you can use different plots to analyze rather than relying on just a single set of data or single conditions to look at. Another very big benefit of Python is it allows you to use open source libraries, where this can be used to generate a variety of input logic, but it's also very useful for adding in additional visualization functionality that's not necessarily included in GPSX by default. Some of the libraries that we tend to use are Matplotlib, Seaborn, and Plotly, where I'm going to be talking a little bit about Plotly later on, but those are all very good plotting and visualization libraries. Another benefit of Python is it allows you to quickly create performance reports or dashboards in each of your layouts, and then you can take that Python script and transport it between either scenarios or layouts. So you can quickly create that report or dashboard in every one of these situations, and it has a consistent and personal look and feel that matches what you're trying to achieve. And another big benefit is Python allows you to quickly compare the performance of several potential configurations where those can either be different layouts or different scenarios. You can take all of that data and compare it in the same plot, unlike using GPSX by itself, where you'd have to run all of those individually, collect the data, and then do your analysis from there. An important thing to note is that Python is included as part of the GPSX Pro Plus license. So if you want to recreate anything that I'm going to be showing in my talk, you're going to need to make sure that you do have that GPSX Pro Plus license. Just as a quick overview, to actually use the Python functionality in GPSX, it's all handled through what we call the Python Script Manager. If you want to access the Python Script Manager, you need to be in simulation mode, and then you can go to that Tools option on the main toolbar and select the Python Script Manager. This is going to open up an interface where you have the ability to essentially manage your Python files, so you can create new ones, edit existing, or delete any that you no longer need. As well, this is where you're going to control the running of all your simulations. So you can select a script and then press run from this Python Script Manager. If you want more details on the Python Script Manager or more how we can use Python for more advanced simulation analysis, we did do a webinar on this about a year ago, and I highly recommend you go back and watch that for a little bit more detail on those topics. But for now, we're going to be focusing on a visualization example, and particularly, we're going to look at how you can compare two different scenarios in GPSX using Python. So we're going to be using Python to switch between two scenarios automatically and analyze the performance of our plant. And the plant we're going to be looking at is a 4-stage Bardinfo process, and we're going to be looking at two distinct scenarios. Our first scenario is going to be a summer scenario where we're just going to tweak the liquid temperature in that scenario so that we have a liquid temperature of 68 degrees Fahrenheit or 20 degrees Celsius in our summer scenario. And then we also have a winter scenario where the difference in that is going to be our liquid temperature is 50 degrees Fahrenheit or 10 degrees Celsius. A couple of other important things to note that I'm going to touch on a bit more details after, but our influent, we're going to be introducing a little bit of uncertainty so that we can get a distribution of results rather than just single results to compare. And then we can do more probabilistic and distribution-based analysis and visualizations. The other thing to note is that all of our other operational parameters are going to be held constant in this simulation. It's just going to be those liquid temperatures and the changes we make in our influent characterization. So the process that we're going to be using is essentially can be visualized as this. We start by running a Python script in our Python script manager. And it's important to note that all the other aspects of our analysis are going to be triggered by this single Python script. So when that's run, we then step into our script and we set all of the random inputs that we want to set for the influent characterization so that we get a variety of different results. After we set those random inputs, then we set our scenario-specific inputs, where that's going to be the specific inputs for either the summer or the winter scenario that we're taking a look at. Then we run our GPSX simulation. I just want to reiterate that Python is going to be actually running every one of these simulations. We don't actually need to go in and press play ourselves. It'll all be handled by the Python script. Once we run those simulations, Python can then go in and collect all the results that we're interested in analyzing and visualizing in our analysis and store those in an appropriate location. And then we can just repeat this process over and over until we have a set number of data points that we want to collect. And then we can do our analysis from there, where we can either take that to an external location or have it all done directly in Python, which is what we're going to be doing in this particular example. So as I mentioned, we want to add a little bit of randomness into our simulation so that we get a distribution of results. And we're doing that in our influent point, and we're going to do it through 5 distinct characteristics. First, we're going to use we're going to create random COD influent concentrations, where our COD is going to have a Gaussian or normal distribution where that's centered around 430 milligrams per liter. Next, we're also going to vary our influent TKN concentration. And rather than use a normal distribution, we're actually going to use a triangular distribution for our TKN, where that's centered around 40 milligrams per liter. Likewise, our total phosphorus is going to use a triangular distribution centered around 9 milligrams per liter. Rather than setting the actual ammonia concentration, rather we're going to set a ammonia ratio, where we're defining that as the ratio of ammonia to TKN. The reason we're using a ratio rather than a concentration value is just we want to ensure that all of our results that we're simulating are actually feasible, so we don't randomly select a set of conditions where, for example, our ammonia is higher than our TKN, which would give us poor results and could mess up some of our analysis. So we just use a ratio instead to ensure that doesn't happen. And we're using a uniform distribution for our ammonia ratio rather than a triangular or Gaussian. So we're going to say that between 0.5 and 0.75, there's an equal probability of any of those ratios occurring. Likewise, we're also going to vary our ortho-P ratio using a uniform distribution, where this is the ratio of ortho-P to total phosphorus, once again, just to ensure we get feasible inputs to our model. And we're using Python to actually drive all of this randomness. So we're using the built-in Python random library, and it has a variety of functions for various different distributions and random number generators that you can use. But we're just using a selection of 3 functions right now. First, for our COD, we're using the Gauss function, where we have to specify what our mean value is and the variance. So we set a mean of 430 and a variance of 100. For our TKN, we're using the triangular function, where we have to set our minimum value of 30, our maximum value of 50, and our mode value of 40. Likewise, our total phosphorus is using a triangular distribution, where we set our minimum to 8, our maximum to 12, and our mode to 10. And then both of our ratios are using uniform distributions, where for ammonia, we're setting it from a range of 0.5 to 0.75, and ortho-P is a range of 0.7 to 0.9. So now let's look at how we would actually go about implementing this in GPSX through Python with a little bit of pseudocode. So what we're just using a for loop essentially to drive all of our simulations, where we're going to run for a set number, predefined number of simulations. Just for transparency, we used 1,000 to get the results that I'm going to show a little bit later, but you could use any number of simulations you want here. So once we start that for loop, we're going to begin by setting some of our random inputs, where that's going to be those distributions that we discussed in the previous slide. We're going to actually set those as input values in our GPSX simulation. And this is done using the recognized GPSX.setValue function, which is built into the Python that is run in GPSX. And in there, you need to specify what the cryptic tag that you're assigning this value to, and then the value itself, where our values are just being generated from those random functions. After we set our random inputs, then we're going to cycle through both of our scenarios, so our summer and winter scenario. The reason we're setting our random inputs first is we just want to ensure that our both scenarios see the exact same set of random inputs, just so we have a one-to-one comparison. So for our scenarios, we're just going to use what we're calling a set scenario inputs function, where we provide the scenario that we're currently running. And since this is just a very simple example, all we need to specify is what our influent temperature is going to be, and that's entirely dependent on the scenario we're running. So if we're running the summer scenario, we'll set our influent temperature to 20, or if we're running the winter scenario, we'll set our liquid temperature to 10. Once we have all our inputs set, then we'll run our simulation using the run sim function. And then after that, we can use Python to actually collect all of the results of our simulation. So we're using what we call the get simulation results function, and we're passing a variable called results to it, where results is a dictionary where the keys of the dictionary are specified with cryptic tags that are in our GPSX layout. So it's all the values that we want to actually collect from our layout, our keys for our dictionary. So we'll cycle through all of those cryptic tags, and then we'll just append the actual value in GPSX to a list that is associated with that dictionary. And to get the value from GPSX, we're just using this GPSX get value function, and you just provide what the cryptic tag that you want to collect is. So now that we know how we're actually collecting all of our data, let's look at some interesting analysis and visualizations that we can perform with that data. So all of these plots I'm showing have been generated with the Plotly library, which is a very good library and has a lot of cool functionality. I'm going to show it a little bit later in an actual demonstration. But if you want to use Matplotlib or Seaborn, as I mentioned earlier, those are also very good options. But what we're showing here is in the top plot, we're showing box plots to differentiate the airflow that's going to tank 2, tank 4, or the total airflow to our bioreactors in both the winter scenario and the summer scenario, where the winter is shown in blue and the summer is shown in red. And one thing you can pick off right away from this plot is that our winter scenario actually has a lower airflow than our summer scenario, despite having the exact same DO set points. And this is just a result of the lower temperature having an impact on the solubility of oxygen. So there's a higher solubility of oxygen in the lower temperature wastewater, so we don't need as much air to meet those airflow requirement, or pardon me, those DO set point requirements. Next, looking at our second plot, our effluent performance comparison, we're once again showing our winter months in blue and our summer in red. First thing you can see is our total phosphorus and ortho-P. There's not much difference between the two scenarios, and that's just a result of we aren't actually doing any biological or chemical phosphorus removal in this layout, so it's going to be a very similar result in both cases. But you can see there is a very big distinction between the BOD and ammonia values in our winter and summer months. You can see that the winter produces much higher concentrations. This is just a result of the lower temperature inhibiting the biological activity, which you would expect to see from the lower influent temperature. I'll just mention that these lower plots are using what's called violin plots, where this is essentially a box plot where the curves represent the density of points at a particular location in our box plot. So where there's a very large curve, that means that we are getting a lot of results at that particular point in our distribution of results. So that's how you would compare two scenarios using Python to create some more advanced visualization. But sometimes you want to just look at a single scenario. And one thing that Python is really good at is you can create a custom set of standardized reports or dashboards that you can use in any of your layouts or any of your scenarios to get a consistent report profile that you can then use throughout all of your anything that you're trying to do. So you can see here we have 4 plots. We have a nitrogen plot where that's just showing how the nitrogen concentrations change across our bioreactor. We have another profiles plot where these are just side-by-side bars representing three distinct concentrations at each point throughout our bioreactor. We then have a table that's summarizing a couple of key variables throughout our process. And then finally, interestingly, we have a pie chart that's just showing a breakdown of how the biomass in the actual bioreactors is distributed. So we have our heterotrophs, our POWs, NOVs, and AOVs. So next, I'd like to show an actual desktop demonstration where we'll look through how we actually got that plot and what it's going to look like in from the output of Plotly. So let me switch to GPSX. And this is that exact same layout that I was using in the previous analysis. So you can see we're in simulation mode. We have our process, which is the 4-stage BART info process. We're using our summer scenario right now, and we just have a constant SRT set point. So since we're in simulation mode, we can open the Python Script Manager by going to Tools and then Python Script Manager. And this will open up your Python Script Manager environment. You can see I've already included two Python scripts in this layout. We have the scenario analysis Python script. Well, what that is, that's how I ran the distribution plots, how I generated those plots. I'm not going to run this right now because it is essentially a Monte Carlo analysis. So we do need to run a very large number of plots, or pardon me, a large number of simulations, and it can be very time intensive depending on the number of simulations that you're looking to run and the complexity of your layout. But it is a very useful analysis, and you can gain a lot of information from running one of those on your plan. The other Python script we have is the make dashboard script, where this is what I use to generate the last plot I showed you in the slides. We're actually going to run this to see what the output would be from the Plotly script, or pardon me, the Plotly library. So you just press the run button, it'll automatically run GPSX for you. And then it opens up in the web browser a dashboard for you with your plot results. And this is just because I'm using Plotly. It saves all of its outputs to an HTML file, so it's going to open up by default in your web browser. You can see that this has all of those profiles that I previously showed. We have our nitrogen profiles, where it's a breakdown of ammonia, nitrate, and nitrite as it progresses through our bioreactors. We have a couple of more bar charts here showing the difference in alkalinity, soluble COD, and slowly biodegradable substrate as it passes through your bioreactors. Then we have a table where this is an interactive table where you can scroll up and down in the Plotly environment, and it's just a summary of a couple of key metrics as they progress through the plant. And then finally, we have our biomass breakdown right here, where this is a pie chart that shows the percentage of biomass that you have in your process. So this purple is our heterotrophs, the red is our POWs, green is AOBs, and purple is NOBs. As you expect, the heterotrophs are kind of the majority of what we're seeing here, but you may want to see what the breakdown is without the heterotrophs. One cool thing you can do in Plotly is you can hide any of the variables that you don't want to see at a given time, and it'll automatically update your dashboard so you can see a breakdown of your biomass when it's not accounting for the heterotrophs. So you can see about 64% is POWs, 30% is AOBs, and about 5% is NOBs. All right, that pretty much shows what I want to show with the Python advanced plotting. So I'm going to give it back to Spencer now just to wrap up with some conclusions on this presentation.
Thank you, Jacob. So just a few final thoughts as we wind things up here. Just that GPSX does contain many different advanced visualization tools that are already built into the software. They're useful for alternate ways to communicate your simulation results. Particularly I find to people who are not, doing a lot of modeling on their own, it's a nice way to sort of tell the story about what the model is telling you. So hit that eyeball button in the results once you've run your simulation. The Sankey diagram and the statistical goodness of fit features that we have in there actually are ones that I take advantage of on a regular basis during model setup and calibration, and that the Python functionality does allow you to basically create whatever you want. It's as Jacob said, there's multiple different libraries out there for plotting and displaying data, and there's some really advanced and very cool things out there that you can get your hands on and just directly export your stuff from GPSX into those advanced features there.